one of you asked me this question about NS having an order greater than DS, right? I think, was it Anirudh?
Yes, sir. Sir?
Yes? Hello?
Sir, I can hear you.
Yeah, did you ask about this NS being greater?
Yes, sir.
Yeah, so let me ask you a question in return. What is the inverse of S? Laplace transform. Inverse Laplace.
So there is no direct formula for that.
So you see, when you have NS greater than having an order higher than DS, when you factorize it, then you are going to get at least something like 1 plus another N1S by DS, where in that case that N1 will be having a lesser order than DS, or you could even have S square S cube plus something something, that is one polynomial plus N1 by DS. And now you think about it, that what is going to happen, what will be the time response of um, such a function, and that will give you a clearer answer of why we normally don't encounter such things when we are dealing with our systems. So coming back to the rules that we have, we will again start off with a very simple rule. So as I said, we have this is, I mean, like say for, I mean, these will be functions of S anyway, but uh, all of these will be, this will be real, this will be real, this will be real, and this will be real. So when I take arguments, therefore, And what are we going to have out here? Because there is a -1. So this will be the basis for our analysis of this rule. We'll now write out Ns in this form. And as I said, N is greater than M. So we will further how does this factored form help? Well, the beautiful part about arguments is that products, when you take arguments, they become sums, and that will be helping us here. So Ns will be equal to so all these z's are the roots of the polynomial ns, and we call them zeros. again what we are saying is that our A zeros and B zeros, they are all positive. So we have when we take the argument of this, then we'll be taking the argument of and these real numbers, A0 and B0 real positive numbers, they are going to contribute 0 in terms of angles.
So it would
we
no
will
longer
have,
be division, right? It would be a subtraction.
right now I'm writing it like this, but what will happen is that you are going to get this is what you are going to land up with. So these two will not contribute anything, and you are simply going to land up with or you can use a different index out here, and this must be equal to got it? So this is what you are going to get. And now let us see how this or what this translates into when it comes to actually drawing the stuff. So out here, All right. Here I had a 0. And I have an S. Let us have an S out here or here. But the basic thing is, on which side of the 0 do I have my S? So for the 0, what will be its argument? Sorry. Okay. This should do. Yeah, for the 0, from here to here, and for the S, from here to here. So S minus 0 will be this. Even if you have, this is for S1, for S2 also it will simply be and when you are measuring the angles, then this is the direction. So my S minus Z is always going to have a
Sir, here is as the root of the characteristic polynomial.
yes, Z is the root. I am trying to draw the plot. Okay, what I am trying to examine is that whether my root locus plot can exist on the real axis. So I have just chosen two arbitrary points, S and S2.
Okay.
S1 and S2, and I'm trying to figure out, okay, if my root locus is lying out here and I have a 0 out here, then what happens? So if it is lying to the left, then then that S minus Z is going to be 180 degrees. If it is lying to the right, then it will effectively contribute a 0 or 2 pi, because in that case this is the angle. So the angle with the origin is this is actually 0 2 pi, whereas in this case this angle is phi. So this is so what have we dealt with till now? We have dealt with, say, the roots are on the of the numerator or denominator polynomial, which we are calling zeros and poles. They are on the real axis, and we have figured out the angles. What about the case when we are dealing with more general form of the roots? So we have something out here. I am considering a point S. I wish to check if this S lies on the root locus. That is, my goal is for the last two slides is to check that given certain zeros and poles, is it possible for the root locus to exist on the real axis? So this is my S. So what will be my call it the position vector if you will. These are the position vectors of the poles or zeros conjugate or phasors, whatever name you want to give it. So these will be the angles. And because of the symmetry, what will be the difference? This will be the two S vectors So what are the angles? This is one angle, this is the other angle. One is positive, other is negative, same magnitude. So they are not going to contribute anything. So now we get back to what we are doing here. This is what we have. So from this summation, we can straight away throw out all those complex conjugate poles and zeros. In fact, all poles and zeros which have imaginary parts, because imaginary poles and zeros will also occur in conjugate pairs. Only thing is they won't have any real part, so they will just lie at plus pi by 2 or minus pi by 2, and they'll occur in pairs, so no contribution. So that means we now have so let us say we have a situation. This is my real axis. So if I have a 0 here and a pole here, and I am looking at this point, so what will happen in this case? To the left, the S is to the left of two roots. So if it is a pole and a 0, then what will happen? There anyway, one will contribute. This is like this. This is like this. Or, okay, just a moment. Let me start with something simpler. So we have two zeros. So what happens in this case? Pi plus pi, 2 pi. So if you have two zeros, then I can safely say that this S is not going to be on the root locus. If it is on the root locus, then it cannot be here, because immediately this condition gets violated. No odd multiple of pi. In this case, these are the three, well, you may call them vectors from the zeros to S, and all are going to contribute pi. So I'll have 3 pi. So S is on root locus. If I take poles also, same logic, only thing is and finally pole zero combination. So what happens? 0 will be contributing positively, this will be contributing negatively, and they'll cancel each other out. If I have a 0, 0 pole, and I have my S out here, as you can see, despite the difference in signs for pole and 0, as long as you have, so we conclude, as long as you have a odd number of zeros and poles, real axis zeros and poles, to the left of the point you are to the right of the point that you are examining, or other way of stating, if the point that you are examining on the real axis lies to the left of an odd number of poles and zeros, then it is on the root locus, because it is satisfying that condition of plus minus r pi. The roots that are not on the real axis, they are not going to contribute anyway. So this is another simple conclusion that we can draw without even racking our heads with too much of complicated theory. So this is the rule that we have. So you see, now we are in a position where we can play a simple game. This is my real axis. You can just try this yourself right now. Where is my root locus? If this is the situation that I have. So I am here. Or let us say I start from here. So is it to the left of an odd number of zeros and poles? No. I move here. Yes. So this is a root locus. Here, no. Oh, sorry. Just a moment. Need to clean up. Yep. Anyway, I'll use another color. So these are the places where my root locus is going to exist. So this is a, now we are in a position of at least clearing up some parts of the root locus business. What we'll be dealing with next is we'll be finding out the asymptotes of the root locus. Okay, and then we'll be finding out break-in, break-out points. We'll be also finding out where the root locus can cross the imaginary axis, etc. So before that, let me at least look at a simple example. If you have a transfer function Ts, so what is my Ns? So this is what we will be looking at. So one thing is, locus must be symmetric about the real axis. We don't have a zero. So based on our knowledge, what can we say? Here, how many? Even number. Here, odd number. So we are definitely going to have a root locus out here. We will also have other branches of the root locus, and we will, in later classes, will discuss, I mean, like, where will they come from? But one thing we do know, that they will be ending at the zeros and beginning at the ending at the poles and beginning at the zeros. So how to reconcile that with what we are seeing here? The actual root locus will look something like this. sorry. I'm using a stress like arrow to indicate the direction. Yeah. I hope this is a different color, green color, all right, blue. Yeah. So this is how the movement will be. This point I'll be discussing in later lectures, where and how to find this point. And as you can see, they are coming in and going to the poles. So this is indicative of a very interesting fact that actually the number of zeros and number of poles are same. Only thing is, some of the zeros are away there at infinity, very far away. So not only can we not see them, not plot them, they also don't affect the behavior of the root locus. And this is an important concept, that poles or zeros closer to the origin, they are, the closer they are, the more capable are they of effectively changing the root locus. And therefore they are the ones that we will be bothering about when we are trying to do design. The other thing is, as you can see when we are writing this ns by gs thing, so what happens if your pole and zero both are same? Now effectively you will say that, well, they'll cancel out beforehand itself while I'm doing my analysis, so why bother about that? Now when it comes to a real system, our problem is things are always not that simple. The zero that we have theoretically calculated, in the practical implementation it may be slightly more than that, and the pole also there may be a slight deviation from what is the theoretically calculated thing. So this can have an effect when poles and zeros are very close together. So sometimes that is kind of undesirable, because if we do not know that a pole and a zero are actually getting cancelled out or on the verge of getting cancelled out, you can get undesirable characteristics which you did not think of. On the other hand, we often use this fact of keeping poles and zeros very close together when we are forced to introduce them to give a new kind of characteristic to our root locus. Then we keep poles and zeros very close together so that their effect on the root locus is not that much, but we can extract something desirable by the addition of these poles and zeros. So that will be all for today's lecture. I will be uploading assignments by myself and given by myself and Professor Samantraya. So you are expected to complete them in around a couple of days and submit. Also, one more thing,